Good morning and welcome again to RMS618 Advanced Statistic Module 3 talk on logistic regression. This is another type of multiple regression that's actually kind of specialized. Its purpose is to predict or explain a dichotomous outcome, a dichotomous dependent variable based on several predictor variables, based on several independent variables. So, in this particular case, our dependent variable, that y prime, is actually dichotomous. So we're going to be predicting whether a set of individual, IVs predicts whether someone's a smoker or non-smoker, or whether someone is Republican or Democrat, or whether a set of IVs predicts likelihood of male or female. So we have a dichotomous DV with continuous, ordinal, or categorical independent variables, and we know we have more than one independent variable. Of course, a large number of observations. We need to readdress our a general study of probability from basic statistics. We know that when we say probability, we're talking about the likelihood of an event. So, whenever we say, hear the term probability, it's just, a likelihood. So the likelihood of the sun going down this evening is very high. The likelihood of me, stuffing a basketball is, of course, very, very low. Don't let that term probability intimidate you, okay? And we know that the probability is the number of times a specific event occurs over the total number of possible events. Now we're going to deal with a term in logistic regression that's a type of probability, but it's kind of a specialized version. It's called the odds ratio, and we're going to abbreviate it OR. It's the probability that something is true divided by the probability that something is not true. So we call it P over 1 minus P. P over 1 minus P, the odds ratio. And we're also going to logistic regression does an entity called logit transformation. And it transforms this particular curve to this particular curve, taking the logarithm of the odds. Now, don't worry about that. That's a mathematical term. But the objective here is to create a linear model, the linear model that we had in multiple regression. Okay? So we're dealing with this logistic regression curve that's actually transformed to something very, very similar to what we did in just regular, general multiple regression. So the objective is to create a linear model, which it does through this thing called logit transformation. It essentially takes the logarithm of the odds. And we're going to be dealing with a dependent variable that's actually referred to as logit P, okay? And it's the natural log of the odds ratio. So this ln is natural log, and the only difference between a log, which we know has a base of 10, and a natural log is that the natural log has a base of 2.72. And again, don't worry about that. This is, this is mathy stuff. But again, you see some familiar things. Okay, you see regression coefficient X, regression coefficient. We're creating a multiple regression equation, but we're doing it to predict a dichotomous outcome. So this odds ratio, this OR, is the ratio of probability of outcome to probability of no outcome. Probability of outcome divided by probability of no outcome. And it's interpreted as a measure of association. It's the strength of association between the predictors and the response variable. So these are, of course, the predictors, the IVs, right? And this is the dependent variable, which is the response variable. So when there is no relationship or no difference, we have an odds ratio of 1, okay? We'll get into that a little bit further when we get into examples. Assumptions. Again, we have assumptions in logistic regression, one of which is the linearity assumption. Linearity between the predictors and logits are dependent of dependent variable. Okay, the linearity assumption. And we see a linear relationship here. We actually see data points going up and to the right, down and to the left. The collinearity assumption also applies. The variance inflation factor needs to be less than 4, tolerance greater than 0.2. So again, we're seeing a lot of similarity to just general multiple regression. Now we have the SPSS data set. We'll take a look at this. What are we doing? Well, we're predicting whether someone is a smoker or non-smoker. So that's the dichotomous dependent variable, using 4 predictor variables, 4 IVs: age, height, sex, and occupation. So we see the generic SPSS data presentation. So we see a continuous variable, a continuous variable, a categorical variable, and another categorical variable, and I believe they're calling occupation a categorical variable as well. It doesn't matter. Our IVs can be continuous or nominal or ordinal or whatever, but the DV is always, it's always dichotomous. It's dichotomous. It's a categorical variable that has only 2 categories. It's a dichotomy. Okay. Now we see the analysis. We bring the dependent variable over into its respective box, and we bring the independent variables over to their respective box. SPSS, in this particular case, prefers to call these IVs covariates, which is fine. Okay, and we're using just general logistic regression. And it's actually specifying that occupation is categorical. Okay, it's, and I personally, I didn't make up this PowerPoint. I don't quite know why gender isn't, indicated as categorical, but it's all good. Another screen. We're going to check classification plots. The Hosmer-Lemshow goodness of fit chi-square. It's going to do a confidence interval for the odds ratio. We have 654 cases, so our N is 654. Now we have a couple of chi-squares, all right? The first chi-square is actually a chi-square test of independence. They don't tell us that, though. They refer to it as the omnibus test of model coefficients. It examines the significance of the model. And this model is indeed significant at alpha 0.05, so p is less than 0.05. This particular test of independence indicates the relationship between the predictors and the predicted. So it's that 2-variable chi-square. It's the relationship between the combined predictors, in this case there are 4 of them, and the predicted variable. So this is telling us that these sig values are very, very small. We've actually rejected a null hypothesis and concluded that variable 1 is dependent on variable 2. There is indeed a relationship here. Our second chi-square is called the Hosmer and Lemshow test. This is a goodness of fit chi-square. We remember the null for the one-way chi-square. What does that imply? Fit, equality, all right? So we have no significant difference between the observed and expected values. P is non-significant. P is greater than alpha. What this is implying is that the model fits the data. And as you see, our p-value is 0.788, which is actually greater than 0.05. So we have a non-significant statistic. In this case, non-significance, of course, implies fit. No difference between observed and expected frequencies. Okay, So in this logistic regression SPSS analysis, you're always going to see these chi-squares. Model summary. Look what we have here. Something analogous to R squared. We have Cox and Snell R squared and Nagelkirk R squared. What's R squared? The amount of variation in Y that can be explained or predicted by the variation in X. So again, this is telling us that this model accounts for about 16.8 to 35.3% of the variation. Okay, so not a lot of relationship between the IV and the DVs. This is the way the data came out. So again, just when you see this, this is just very analogous to the R squared that we deal with in regular multiple regression. About 88% of this model is accurately predicted. Okay, so this model accurately predicts about 88.4% of smokers, which is pretty high. We have coefficients now. This is our output. Look, this should look familiar to you. And it puts the equation together. And if you notice, it excludes, for some reason, occupation, probably because it's non-significant, okay? But, as we see, we have significant predictors of smoking. Well, again, this is the DV. We have 3 significant predictors. These are our odds ratios. These are our odds ratios. So we put an equation together here. The logit P, which is actually synonymous with Y prime, the DV, is 17.239, which is the Y-intercept, minus 0.394, that's age, minus 0.152, height, minus 1.357, gender. Now let's take a look at these odds ratios. Let's take a look at these 3 odds ratios. What do these mean? Now you see these are all less than 1. This particular odds ratio for age implies that a 1 unit increase in age decreases the odds of being a smoker by about 32.6%. So 1 minus 0.674 is 0.326, or 32.6%. So a 1 unit increase in age decreases the odds of being a smoker by 32.6%. Let's look at the height variable in terms of odds ratio. Okay, a 1 unit increase in height decreases the odds of being a smoker by 14.1%. So again, a 1 unit increase in height decreases the odds of being a smoker by 1 minus 0.859, which is 0.141, or 14.1%. Let's look at gender. This is really, really interesting. Okay, the odds of smoking if you are female are 0.257% lower than for men. The odds of smoking if you are female are 25.7% lower than for men. What this implies is that the likelihood of women being a smoker is actually lower. There are more men smokers than women. Okay, there are more men smokers than women. And if you look at CDC data out of Atlanta, it will verify that smoking prevalence is indeed higher among men than women. Okay, so again, we have this prediction equation, predicting whether someone is, the likelihood of someone being a smoker or non-being a smoker depending on age, height, and gender. Okay. Reporting results in APA format. Okay. Report the assumptions. Let's see what this this all says. The chi-square goodness of fit was statistically significant, indicating a good fitting model. Okay. Now these are actually the results of the omnibus test. Okay. So this is actually not the measure of model fitting. It's more a measure of model significance. Okay. But that's all right. I didn't put these PowerPoints together. This model accounts for 16.8 to 35.3% of the variance. Okay, that's a good state. The predictive accuracy of the model was 88.4%. The model accurately predicts 91% of non-smokers. Age, height, and gender were found to be statistically significant. And like I said, an increase in 1 year of age decreased the odds of being a non-smoker by a factor of 0.674. Okay, so I think the purpose of in writing your papers for this course, it's very important to present the results in this particular type of format. Okay. Perform logistic regression on this particular data set to determine whether prior score and experience, so we have 2 IVs in this case, are predictors of passing a health test. So the DV is again dichotomous, pass, no pass. Describe and interpret the results. It wants us to talk about the assumption of collinearity, the crude and adjusted odds ratios, and the 95% CI. How much variance is explained by the model? We know it's those R-squared estimates. What's the regression equation? This is all pretty basic stuff. Interpret goodness of fit tests. Describe the predictive accuracy of the model. So it's taken us through the steps. Okay, we have our SPSS screen. We have pass or fail as the DV, and score and experience, that EXP is experience, as the independent variables. Crude odds ratio versus adjusted odds ratio. Okay, we need to remember that distinction. The adjusted odds ratio takes into account confounds. So if the crude OR and the adjusted OR are similar, we know that there's not really a whole lot of effects of confounds. If the crude OR and adjusted OR are not real similar, we know that OR is being affected by other confounding variables. So as we see with the variable experience, we have a crude OR of 1.155. Okay, it gives us a B of 0.144 and so on. The variable, the IV experience, is a significant predictor because 0.047 is less than 0.05. The confidence interval, there's about a 95% likelihood that if we were to take repetitive samples, our odds ratio would fall between 1.002 and 1.331. For the IV score, we have a non-significant predictor. P is 0.386. P is actually greater than 0.05. And we conclude that we have a non-significant predictor. B is 0.234. Our crude odds ratio is 1.263. And there's about a 95% likelihood that if we were to take repetitive samples, our ORs would fall between 0.744 and 2.143. So on your papers, you're going to have to recognize and report on the distinction between crude OR and adjusted OR. Okay, just remember. The adjusted is just adjusted for the possible effects of potential confounding variables. Interpret crude and adjusted OR and 95% confidence interval. Okay, we just kind of did that, but look at this. For the IV experience, our crude OR and our adjusted OR are pretty similar, okay? There's about a 95% likelihood, again, that if we were to repeat this an infinite amount of times, that our crude OR would be between these values. And the same applies for this particular situation on experience. Okay, so there's a lot of similarity. And so what this is saying is that not a whole lot of effects of other confounding variables with this particular IV, with experience. And we see experience is significant at alpha 0.05, so P is 0.043 for the IV score. A little bit more, first of all, score is non-significant. P is greater than alpha, and we see a little bit more discrepancy, but not that much, between crude OR and the adjusted OR. And again, we can interpret the confidence intervals accordingly. You need to remember from basic statistics how to interpret CIs. Okay, in this particular case, there's about a 95% likelihood that if we were to take an infinite amount of samples, therefore computing an infinite amount of ORs, that our ORs would fall between this number and this number. Okay, and again, you see we put the equation together. The dependent variable equals the y-intercept, which is this figure, plus 0.147 experience, plus 0.288 score. Logistic regression. So you see a lot of similarity between this and just regular multiple regression. Is the assumption of collinearity met? I believe the answer is yes. Look at our collinearity statistics. Our tolerance is greater than 0.20. VIF is certainly less than 4. Looks like we're doing good on the collinearity score. How much variance is explained by the model? Again, we have our two types of R squared, Cox and Snell, and Nagelkirk. Okay, we see again not a whole lot of relationship between, in terms of shared variation. So it's about 27, about 19.9% to 27% of the variation in Y prime, of course, can be explained by the variation in the independent variables. All right, so again, pretty standard stuff. Again, we have our chi-squares. Chi-square number 1, this two-way chi-square, this test of independence. We see non-significance here. This is indicating that the overall model is non-significant at alpha 0.5. In this particular case, P is greater than alpha. So we would conclude that the combined predictors don't predict the outcome real well. And we see one of those predictors that was actually non-significant. And we see that the data indeed fits the model. Okay, the null is true in this case. P is greater than alpha. So we have a fitting model. We have a pretty well-fitting model, but not that highly predictive. Also is indicated by the R-squared estimates as well. So there's a lot of things, that we consider, with this logistic regression. Describe the predictive accuracy of the model. It accurately predicts about 73.1%. Okay. When do we use logistic regression? Okay. Dichotomous dependent variable, continuous or ordinal or categorical independent variables. Again, as many subjects as we can. We essentially perform most of the assumptions that we do in regular multiple regression. We work with the odds ratio. Okay, anything greater than 1 is higher association. Anything less than 1 is a lower association. We do a logit transformation to sort of mock linearity. And using SPSS for logistic regression, the steps are pretty well outlined in your instructions, so just follow your nose. and do the logistic regression exercise. And again, if there's any questions, get on the discussion board and ask your questions or email me. Okay, this concludes our session, Module 3, Logistic Regression. We will see you next time. Have a good day.